use mathematical induction to establish Leibniz's rule given by this. For the nth derivative of a product of two differentiable functions f of g and g of g. So problem suggests some clue. Note that the rules is valid when is equal to 1. Then, assuming that it is valid when n is equal to m, where m is any positive integer, show that n plus 1 derivative of f times g, m's derivative of f times first g prime plus m's derivative of f prime g is f times m plus 1 derivative of g plus summation k is 1 to m choose k plus m choose k negative 1 times k's derivative small f here, then m plus 1 negative k's derivative of g plus m plus 1 derivative of f times g. Finally, with the add up the identity, in section 3, in exercise 9, we have studied this identity valid or so just use this identity, show that m plus 1 derivative of f times g is equal to here f times g m plus 1 derivative of g plus summation k is 1 to m plus 1 choose k's derivative of f here, m plus 1 negative k derivative of g plus m plus 1 derivative of f times g. So using this identity here, then we get this. Here this part will be replaced by this m plus 1 choose k because by this identity. So this formula can be rewritten like this. Then we just arrange the these two terms, first and last term, by using the summation, using starting index k is 0 and ending index m plus 1. Then we can unify the we get this result. So if n is 1, so we are going to use mathematical induction. First, we're going to check the case of when n is 1. The f of g times g of g prime is equal to f prime g times g of g plus f of g times g prime of g, which is equal to this. You already checked it previously here. Then we suppose that this statement holds for the case of n. So which means that for any n integer which is larger than or equal to 1, this formula holds. We assume that. Then we are going to show that for the case of n plus 1 here, to show that we are going to use this identity here, or definition. So n choose 0 n plus 1 choose 0, n choose n plus 1 choose n plus 1 is are all 1. So here n plus 1 derivative of product of f of g is equal to the prime of this function. So here to differentiate it, this, then we get this result here, because this part is the product of two functions, case derivative of g and negative case derivative of g. Here there are some typos here, and k negative and negative case derivative of g here. So we get this, and further rewrite this by using this fact. Then we get this here. Because this has two terms here. We have to part by separating the summation here. Oh, here is the typo. Okay, and then we rearranging the index here by pulling out the case of k equal to 0 here, and also from this, the case of 0 is expressed first here, the next here. Then here okay, we get this result by arranging these terms here. Which is the result we desired for this problem. In the previous here, this part, we showed that we straightforwardly derive the coefficient Cn for the Taylor series of the product of f of g. So we get this result. But there is another way to compute this expansion. In fact, series 4 is the same as the series obtained by formally multiplying the given series we have in the expression 1 term by term, and collecting the resulting terms in the same powers of g negative g naught. In other words, here you can see a product of f of g times g of g here, and on the right hand side, the product of their series expansion, which means that summation n is 0 to infinity an times g negative g naught to the n for f of g, times summation n is 0 to infinity bn g negative g naught to the n for g of g here. So which should be equal to this series expansion by assumption. So for this, we compute by using the Taylor theorem just previously here, expression 4, series 4. But this actually we can get compute by just computing term by term for the former part and the second series, and then collecting the resulting terms in the same powers of G-negative genome. Okay, here the left hand side here, for the f of g, series this function can be expanded to f of g naught divided by n 0 factorial times g negative g naught to the 0, which means the constant plus the first derivative small f divided by 1 factorial g negative g naught to the 1 plus second derivative of f divided by 2 factorial times g negative g naught squared here, plus 3 terms for this series expansion of f of g. Then here we have 3 terms for the series expansion of g of g here, same form but replaced by g for f here, and then just product multiplying term by term. First, we when we consider the constant comes from both series, then we get this, which is the 0 powers of g negative g naught here. It's just f of g times g of g. Okay, f of g and g of g, which is exactly a sub 0 and b sub 0, so which is exactly this term. And then next move to the first order of g negative g naught here, and then we choose constant from the series of g of g here, plus and constant for the f of g, and then here first order of g negative g naught, then multiply and compute to get this. So like this, we have the same result for the product of f of g and g of g. It is called the Cauchy product of two given series.